So I hear a little bit of distortion. I'm going to go ahead and mute where that's coming from. So today's inclusion question is about spring break. What's one thing you did that required some knowledge of science? What's one thing you did that required some knowledge of science? Go ahead and put that in the chat. We'll start in about 1 minute. Sign-in sheet is posted. Adam has posted it in the chat, so please sign in. And this is the sign-in sheet where you can put the starting and end time you will be present. Looks like we're getting our regular attendees. Welcome back. We appreciate you guys keeping your minds open, giving us more and more opportunities to share what we've learned.
Is that an eclipse background, Michael, or what? No, that's the Earth, huh?
It's one of the default included backgrounds. Yeah, it's the Earth and the sun.
I still want to know how some people can have non-default ones. It must be that they had files before that got locked down or something. I don't know. Least of our problems.
Yeah, those people might not have upgraded or updated something, and now they get to put whatever they want.
Mm-hmm.
I'm jealous. All right, we've got our first response to the inclusion question. The inclusion question is, what's one thing you did over spring break that required your knowledge of science? And a teacher is responding, Carmelita is responding, teaching biology and interactions credit recovery during spring break. A teacher would definitely need the knowledge of science to do that. Carmelita's got me thinking about what summer school will be like this year. Will it be online? Will it be in person? Will it be overflowing with thousands and thousands?
Do you have an idea, Mike, if what will happen to our summer school? Is it face-to-face or it's still a remote learning?
I was just asking that question out loud. I've asked IHAM, I've asked my principal, and right now they just don't know. I think a lot of principals are waiting to see what it's like in person.
All right.
Have you heard anything?
CAST?
The CAST?
Yeah. How about CAST? Do you have any idea if it will, push through or it's still?
I know for Gardena, we're scheduled to give the CAST. Gardena High School scheduled to give the CAST starting that week we come back. And I don't know anything more than that. I mean, the students will probably be taking it at home if they choose to stay at home, and those who come to school will do the same. But I'll try to follow up on that and post it on our school group.
Right, because I asked my administrator about it, and they say that as of now they didn't receive any final answer if they're gonna facilitate this or not. So
Okay.
that's why. she said that we're still waiting,
Mm.
so we don't have any schedule yet when I asked it. All right, thank you for that.
All right, let's continue. I see hiking in Arizona. Pick trails at higher elevations, knowing the altitude tends to reduce temperature. Tracy surfed over spring break. She had to keep abreast of the tides and wind projection for the best waves. Flint was building a water well, still trying to clean up the well water at my father-in-law's house. Used different concoctions to try to get sap off my car. Eric says, ugh, sap. Cora says, I kept track of the daily temperature. Irene says, went hiking, checking the temperature and the distance. Cora says, I went to review with my student during advisory for science. What? Oh, I want to review. What should I review? So the CAST blueprint is on our interactions group updates. So I'll go ahead and try to meet with Adam and Aham and see if we can get a little more clarity on what the CAST requires teachers to cover from interactions. Cooking for the family. Relaxed and decompressed. Freezing points in Illinois for outdoor flowers. Great. Thank you all for sharing. For myself, I realized that the sun is causing the greenhouse effect in my car more often than before because there isn't as many clouds, and that infrared radiation is really getting trapped in my car, making my car seats nice and warm. Another teacher says, homemade from scratch garlic bread, food science, measuring, etc. That sounds delicious. All right, let's go ahead and move forward. So we're going to have some norms where we start and end on time. Stay muted until the initial presentation is over. And then during discussion period, unmute yourself when speaking, sign in and sign out on time. Today's objectives is to have a overview of Unit 3 Investigation 2. Our topic is going to be about analysis of learning targets. Those who are familiar with mastery learning and grading, we're going to touch upon some of those concepts today and integrate that with interactions, and then observe and analyze some artifacts from my classroom, and then maybe share out some teaching strategies or some suggestions and advice for mastery learning and grading with interactions. And then if there's time, we'll walk through the interaction teacher group resources. Here's our agenda. We did our inclusion. We're going to go through an investigation overview, then go through learning targets, artifacts, and then grading practices, and then a tour of the resources. We've covered our inclusion question, and Unit 3 is about what powers a hurricane. We need, your students will need these 3 concepts to have a foundation to base their Unit 3 concepts that they will acquire. All of these about water molecules and how matter can change phases due to changes in energy and molecular motion, and those changes can impact a surrounding of a system. What powers a hurricane? It starts with the polarity of water due to the differences in electronegativity. Those differences can be stuck on a molecule in the gaseous phase, moving at very fast speeds, and the space between the molecules are far apart in the gaseous phase. In the liquid phase, molecules are more closer together, moving slower than the gaseous phase. And in the liquid phase, intermolecular attractions can occur, such as hydrogen bonds between the partial positive and partial negative charges of the water molecule. When it rains or when there's rainy weather, the water vapor can condense. The water vapor can condense, causing a conversion of energy. The kinetic energy of each water molecule can transfer out of the molecules and into the air when water condenses. When water condenses, those intermolecular bonds form, and we learn from Unit 2, when bonds form, excess energy is transferred to the surroundings. This bar graph kind of sums it up nicely. Water molecules before condensation have high kinetic energy. The air that's surrounding the water molecules has low kinetic energy. When water molecules condense into the liquid form, the kinetic energy is transferred out into the surrounding air. And that is what powers a hurricane. We'll now go into Adam's portion of the presentation. Unit 3, Investigation 2. So I'll go ahead and stop sharing. Adam, do you need a few more seconds?
No, I'm ready.
Okay. Here's Adam, everyone.
Right. So Mike gave us a pretty solid introduction to what I'm going to be covering. Get my screen shared. So this is where we left off. Unit 3, Investigation 2. Now, we know, we are fully aware that most people are not on Unit 3 and are not on Unit 3 Investigation 2 and probably will not be by the end of the year. But we are trying to give you a big overview of the entire curriculum by the end of this year. So we will finish Unit 3 today and then Unit 4 over the next couple of meetings so that you can see where you're going. So even if you don't get to Unit 3 this year, even though you probably won't get to Unit 3 this year, you can see where the curriculum is headed. Also, please keep in mind that we are recording all of these and we are posting them online. So when it does become time for you to start Unit 3, you will be able to refer back to these. Now in Investigation 1 of Unit 3, we asked the question, what makes water special? And of course, the overall driving question for Unit 3 is what powers a hurricane? In Investigation 1, we asked, what makes water special? And students, throughout this investigation, they developed a model to explain what holds water molecules together in the liquid state. They started by comparing liquids to gases and observing that while gases are compressible, that's something we established early on in the course. When we measured the mass of gases, liquids are not compressible, at least much less compressible than gases. We saw how water is a polar molecule versus hexane, which is nonpolar. We observed that by watching a stream of water bend toward a charged object while hexane did not bend. We saw how the effects of the properties of particles, their mass, their polarity, their molecular structure, affected the macroscopic properties, such as viscosity and boiling point. We learned about electronegativity. We saw that oxygen is more electronegative. Oxygen is more electronegative than hydrogen, and that's what leads to the polarity of water, because the electrons tend to be distributed more toward the oxygen end of a water molecule than the hydrogen end. We saw how polar molecules arrange themselves and why they arrange themselves that way, how nonpolar molecules attract each other. And we saw the arrangement of particles in solid, liquid, and gaseous water is due to polarity. And also the relatively high boiling point of water is also due to the polarity of water. Finally, students did reading where they learned about surface tension and about how surface tension is caused by the attraction of water molecules to each other. Now, in investigation 2, our driving question is going to be what happens to the energy of water molecules during hurricanes? Students are going to analyze evidence to make claims about what happens to water molecules during phase changes from solid to liquid, liquid to gas, gas to liquid, liquid to solid. They'll also use a simulation to analyze and develop a model of the relationship between potential energy, phase changes of water, and decomposition of water. Remember earlier in the year, we did a demonstration and an experiment with electrolysis where students actually used electricity to force water to break apart into hydrogen and oxygen. We're going to revisit that. And students are going to use the relationship between changes in energy and phase changes to explain where the energy for a hurricane comes from, to finally answer this unit driving question, what powers a hurricane? We start with activity 3.1. So if you have not, oops, this is an old slide. Wrong with that. There is no planning guide. However, there is, the lessons are posted on Schoology for you to download. So if you need to download Unit 3 Investigation 2, you'll go to the Interactions Teachers group. Once again, go to Interactions Lessons and Summative Assessments, the orange folder. Click on Unit 3, and you'll see Investigation 3.2, what happens to the energy of water molecules during hurricanes. You can download the whole investigation at once to one of your courses and follow along with the activities that I will be describing. We start with activity 3.2.1. What does boiling do to water molecules? We're going to look at what boiling actually is. We start with the introduction. In the introduction, students draw an initial model showing what happens to water molecules when they're heated up and boil. In the introduction, they're just drawing an initial model. Now, one thing that you'll notice is that by the time we get to Unit 3, a lot of these activities are more open-ended. So we're not providing the same level of scaffolding that we were back in Unit 1. For example, when we tell students that we want them to draw a model of what happens to water molecules when they heat up and boil, we don't give them a template. We only give them this blank canvas to draw their models on. And most of the models, remember back on our initial model, we gave them a template with a Van de Graaff generator, and all they had to do was put in charges and show things attracting and repelling. Well, at this point, we're expecting students to start drawing their own models more or less from scratch. In the next part of this activity, testing boiling water, we're going to use cobalt chloride test strips. Now, cobalt chloride test strips, they're little blue paper strips that are, they've got cobalt chloride on them. Cobalt chloride, it's a blue compound. When it's exposed to water, the blue strips turn light pink or white. So for example, here is the lab that students are going to conduct, or if we're online, they're going to observe. So they're going to take cobalt chloride test strips. I'm going to skip through this. You can see that it turned white or pink when it was exposed to water. Okay. We see that when the cobalt chloride is put in water, it turns pink. We see that when it is put in, we're going to see water condense, or we're going to see a liquid condense on this watch glass that's sitting over boiling water. We're going to test that compound and find out, yes, it is indeed water. Okay, so students will conclude that this compound that formed on the watch glass was water. And then finally, we'll just hold a cobalt chloride test strip over boiling water, and we'll see that it turns light pink. And that will tell us that there is water, or that will tell students that there's water in the air above the boiling water. Okay, so we see water existing in all of its forms, solid, liquid, and gas. We are going to compare that then to ethanol. We find that when we test ethanol with cobalt chloride, our students will find that when they dip their cobalt chloride strips in ethanol, it does not change color. Okay, and then likewise, when they test it in acetone, it does not change color. So what we're establishing is that this is a valid test for the presence of water. So we find that there's definitely water in steam. There's definitely water in condensation. If you're doing this in the classroom, you can use any liquids that do not contain water. So Mike used acetone and ethanol, but as long as you use something that is not water-based, you will get a good demonstration there. In the next activity, again, these would be classroom activities, if you can do them. Otherwise, we're going to see Dr. Mayer demonstrating how she's inflating a balloon with steam. So she has water in the flask, she inflates the balloon, and then you would pass this around, clamp it off, and then you would pass it around the classroom. And what students would be able to observe, and what she's showing, is that there is a puddle of water that forms in the balloon. You can also observe that it deflates as you take it off the flat, or it doesn't deflate. You can observe that it shrinks as you take it off the flask. You could observe the change in temperature. Students will make all kinds of observations when you can do this demonstration in the classroom. So here we see, okay, I can inflate a balloon with steam. So is that the same as, is steam, if steam is water, is that the same as hydrogen and oxygen? So we go back to our demonstration that we've already seen. We see that when we touch a flame to, well, we would see that if we touched a flame to a steam-filled balloon, it would just pop. And when we touch it to an oxygen and hydrogen-filled balloon, it goes up in a burst of flame and sound. And so we see that we verify that steam is in fact not the same as oxygen and water. It is where we're repeatedly trying to show that the molecules that make up water vapor are the same as the molecules that make up liquid water. Now, at this point, students will revise their model of boiling water, and they will try to explain, why did the balloons behave so differently? The balloon that was filled with steam just popped, and the balloon that was filled with hydrogen and oxygen, well, they would say exploded, but there was a chemical reaction that took place there. The next activity is 3.2.2, how hot can water get? Now, how hot can water get? We are focused on the energy changes that occur when water is heated. We start with a well, not a driving question, but we start with a question: which is hotter, water that has been boiling for 1 minute, or water that has been boiling for 15 minutes? And it seems logical to say water that has been boiling for 15 minutes is hotter, but then students will do an experiment where they take ice in a beaker and they put a temperature probe in there or a thermometer, and they put it on a hot plate and they measure the change in temperature over time. And what they will see is that as a solid, the temperature slowly increases, but then while it's melting, it stays pretty close to 0 degrees Celsius until it's melted. And then it starts heating up again until it gets to 100 degrees Celsius. And while it's boiling, it stays pretty constant at 100 degrees Celsius. Students are going to draw a data table showing this, and then they will also draw a graph showing a heating curve of water. This is a pretty common, pretty typical activity to do in a chemistry class, where you want to show energy changes or temperature changes as energy is consistently added to water. And that's what's happening here, is that it's sitting on a hot plate, so you have energy continually going into it. So then the question is, why is it at these points the temperature is not increasing? Okay, at the melting point and the boiling point, why is the temperature holding constant? We're going to look at a simulation, breaking molecules versus pulling molecules apart. We're going to come back to the simulation several times. So in this simulation, you can choose to pull 2 non-polar molecules apart, pull 2 polar molecules apart, pull a non-polar molecule apart, or pull a polar molecule apart. So what students will see is that pulling 2 non-polar molecules apart is pretty easy. It does produce some change, or it does result in some change in potential energy. Okay, there's a slight increase in potential energy. They see that when you have polar molecules, you try to pull them apart, it takes a little more effort. There's more of a change in potential energy. And of course, they are attracted back to each other in that configuration. You try to pull a non-polar molecule apart. Okay, in this case, you are breaking molecular bonds. Not just intermolecular forces, but breaking molecular bonds. See, it takes a lot more force, a lot more energy. You're getting a greater change in potential energy. And if you want to pull a polar molecule apart, well, that takes a lot of, that represents a large potential energy change. What students will notice is that there's a greater increase in potential energy with breaking a molecule versus just pulling 2 molecules apart. That there's a greater energy change with polar molecules than with non-polar molecules. And they're actually going to rank these four categories as to how much energy it takes to pull them apart. And then they're going to relate it back to this heating curve. Well, what is the effort that it takes to pull molecules apart? What does it have to do with what's happening on this heating curve? This is where we're going to refer back to electrolysis. So we're going to remind students of the activity they did where they ran electricity. They used a 9-volt battery to create an electrolysis apparatus where they actually separated the oxygen and hydrogen from each other in water. And then they tested them, found out one was hydrogen, one was oxygen. And what we found, or what we will find, that is it takes a lot more energy to undergo electrolysis than it does to cause water to boil. Students are going to draw a model of electrolysis showing bar graphs, and then they're going to compare that to boiling water. Okay, how much energy does it take to break bonds versus how much energy does it take to separate molecules from each other? They're going to do a reading at this point. They're going to do a reading at this point where they're going to read about why is temperature constant during boiling. So it's the sort of thing that's kind of hard to just figure out by interpreting data. So they will tie their ideas together in this reading. As part of the reading, they're also going to draw models for why temperature remains constant for phase changes. They're also going to draw a model. Well, they're going to draw a model for water molecules boiling, and then they're also going to draw a model for ethanol boiling. They're going to try to explain why ethanol has a lower boiling point, and it's because it is there are lower intermolecular forces. So they're relating everything back to these intermolecular forces. Now, when we get to activity 3.2.3, this is where we're going to tie all of these ideas into that driving question. What powers a hurricane? We're going to start by learning about condensation. So far we've been learning about boiling, evaporation. We're going to reverse that, learn about condensation. Students are going to draw an initial model. So basically, hopefully they can just say, okay, so if evaporation is liquid changing to gas, condensation is gas changing to liquid, it's just a reverse of the same process, and the energy changes are reversed. Students are going to relate condensations to drops of water forming in a hurricane. So when you have all the big clouds and you have condensation occurring to form these big drops of water, what energy changes are taking place? What's happening to the environment? And we're going to refer back to the simulation. We can refer back to this simulation and focus now on the potential energy. Oops. If we focus on the potential energy, we want to say, well, what happens to the potential energy when water molecules move together? So if we look at two polar molecules, what happens to the potential energy? If I let go of these and they move together, I can see potential energy dropping. But what does that mean? If potential energy drops, we've already established that energy is conserved. So if potential energy drops, what does that mean must be happening in the surroundings? And the answer, of course, is that the energy of the surroundings must be increasing. So it's actually forming of the drops of water inside the clouds is what provides the energy to power that huge hurricane. So then the question is, well, that's hardly any energy. How can that power a hurricane? And the answer is that it happens over a huge area, huge volume. Hurricane involves the forming of many, 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 many droplets. So then we ask, well, what if instead of condensation, now what if we had hydrogen and oxygen combining to form water drops? And of course, in that case, the energy changes would be enormous. That's basically like rocket fuel, hydrogen and oxygen combining. So it would be much more energy. There would be much more energy involved if there were chemical reactions than if there were physical changes. So we show that a hurricane is powered by these physical changes, not by chemical reactions. And finally, we kind of relate this back to way back to unit 1, when we were trying to charge all those objects, and if we were doing it on a humid day, we found that it was really hard to charge them. And this is what Mike was referring to earlier. And we can we can see that when there's more water in the air, it becomes a lot harder for objects to hold an electric charge. Mike?
Great. Thank you, Adam. Let's go ahead and transition to learning targets. Learning targets are a grading practice, an instructional tool of mastery learning and grading. And just to see how many of you are familiar with mastery learning and grading, let's go ahead and do a quick poll. Let's see here. Okay, we'll do that from this computer. And let's just do this in the chat. Okay, on a scale of 1 to 4, on a scale of 1 to 4, 1 representing very little or no experience with mastery learning and grading, and 4 representing ample experience with mastery learning and grading. Where do you stand? Okay, so in the chat, there's a question I'd like for all of you to answer, and just go ahead and do a quick, let's do a quick check in the room where we're at. Okay, we've got some 2.5, some 2s. Okay, so we won't be starting completely from scratch, which is a positive thing. Okay, we got a 1.5. All right, so thank you all for sharing. I'm going to do my best to keep it clear and not overwhelm you with mastery learning and grading. I know Gardena High School has had all the staff get certified. I'm certified, which means I've done 8 hours of asynchronous work. So in no way am I an expert of mastery learning and grading, but I do have a basic understanding of the process, and we're just going to cover one aspect as part of our coverage today, and that's going to be learning targets. Just going to make this quick adjustment. Okay, so let's go ahead and share my screen and start from the beginning. Okay, learning targets. Let's put some closed captioning. Put it in English. What is a learning target? Well, in mastery learning and grading, what I've learned is that learning targets are specific essential skills for the class you are teaching. They are based on state standards, and they can be measured by multiple formative assessments. What is the benefit of learning targets? Well, it uses student-friendly language. Standards are made easier for students to attain. It can be used to help the teacher keep track of student progress, as well as students, and can be assessed. Learning targets can be assessed in multiple means. So it won't be just one quiz, one test, one task. It'll be multiple opportunities for the students to show their mastery. So I've spent some of spring break as well as before spring break to create learning targets. Now, these are not official learning targets from Michigan State University or the writers of Interactions. These are just from my own experience with my training in mastery learning and grading, as well as my experience teaching Interactions. And I was able to hone Unit 1 and 2 into 9 learning targets. And that should help guide your understanding and your learning of what it is. And I'm going to combine this with student artifacts so you can get some concrete examples of how to use learning targets to track your students' progress, help your students attain the state standards, and provide multiple opportunities and more equity for your students in your class. I'm going to go ahead and give you the entire list. This slide just shows one. Let me find my chat. Sometimes it hides. There we go. And thank you, Ms. Fuentes, for your kind words. Unit 1 and 2 learning targets. So go ahead and click that link in the chat, and I'll give you a little tour of the list. So in this Google Doc, you will see at the very top a list of performance expectations by unit. You don't have to click on that now because the focus is learning targets. Was everyone able to access the Google Doc? Maybe you're all going to populate in a moment here. On my screen, you can see that Unit 1 has a learning target. Great. There you all are. A learning target based on HSPS 2-4, where students can say, I can use Coulomb's law to describe and predict the electrostatic forces between objects. Now, that's not the entire PE. It's been truncated, so it's easier for students to focus and easier for teachers to teach. Along with the learning target is a rubric, so we know, so the teacher knows and the student knows if there is proficiency, if there's an achievement of proficiency. So let me give you an example. So on a 4-point scale, a 1 is the lowest, because if a student receives a 0, it's detrimental to their grade. A 1, it's not going to be giving away A's and B's for lack of effort. It's just a low score. It's an indicator that tells you that the student does not describe and predict the electrostatic forces. It does not explicitly refer to any evidence from the investigation. A 2 for this learning target is there is some description and prediction, and there is one piece of evidence. A 3 is a clear description and prediction of the electrostatic forces, and is supported by 2 pieces of evidence from the investigation. A 4 is a clear description and prediction and 3 or more pieces of evidence from the investigation. Now we're going to go over this first learning target in great detail with student artifacts to kind of make it very clear what it looks like in the classroom, at least in my classroom. At your own time, on your own time, you can look at the other learning targets. We have learning target 2, learning target 3, learning target 4, and that's it for unit 1. And some of you might just use unit 1 for the entire school year, and that's okay. You're teaching online, you're teaching for the first time. Maybe you want to try out mastery learning and grading, so feel free to stick with all of unit 1 for the entire school year. But if you have time remaining, go ahead and move on to unit 2. Unit 2 is on page 3. Learning target 5 is about models. Learning target 6, it's about models. Learning target 7 is about investigations. And learning target 8, it's about models. Do you notice a pattern here? Learning target 9 is about explanation. So this is a very dense document. Please don't get too distracted. I just wanted to show you that there are learning targets and rubrics available for you to use. And I'll show you how I use them in my classroom. And I'm not an expert. I just got certified last month, and I'm transitioning into mastery learning and grading at hopefully a realistic pace. I'm not going to do an entire overhaul because that would just mean starting from scratch. Okay, let's start at Unit 1, Learning Target 1. I can use Coulomb's law to describe and predict the electrostatic forces between objects. If you looked at that list of learning targets, 5 out of 9 of them focused on the skill of developing and using models. 2 out of 9 were focused on constructing explanations, and 2 out of 9 were focused on conducting investigations. So interactions is very heavy on modeling. And what's nice about modeling is that it can incorporate explanations in the written part of the model. Let me show you what I mean. So if you're trying to measure a student's ability to explain or to model, sometimes there'll be some overlap because models are used to explain the cause behind phenomena. Explanations, written explanations, are also used to explain the cause behind phenomena. So they can be interchangeable. But what a difference is that models don't necessarily cite evidence. Explanations more commonly do. Explanations don't always have to have evidence either, but that makes it a weaker explanation. So that's one difference. Models don't always cite evidence. It's kind of redundant there. Another difference is that the models and explanations don't contain images, usually, but models always have images, something visual, thinking made visual. And models can contain explanations. So in my examples, you're going to see sometimes the assessment for an explanation is going to contain a model. It seems to be working for me in my classroom. Let me show you some examples. So for learning target 1, Coulomb's law, a description and prediction of the electrostatic forces between objects is going to have 4 assessments. And then I will make a final decision what the student is going to receive as an overall score. The 4 assessments for learning target 1 are going to be the revised Van der Graaf and PyPans model, something I created where there is a balloon and hair phenomenon. Assessment 3 of this learning target is when the Scotch tape magnet and spheres are in an activity, and the students create an explanation of that. And then assessment 4 is the revised Scotch tape model. So each time the student does one of these tasks, I will see how close they are to meeting learning target 1 with mastery, proficiency, approaching proficiency, or incomplete. And we're going to use one of my students, Lamb. Now, Lamb observed this phenomenon, and she drew an explanation for it. The question in Unit 1, Investigation 1, Activity 1, Question 4 was, now that you see what happens to the PyPans after the Van der Graaf generator is turned on, make 2 drawings to show what caused the PyPans to behave the way they did. Let's just read the highlighted parts. She's able to say the same sign repels one another, different signs attract another. She's able to say Van der Graaf and aluminum pans have the same positive charge, so they repel each other. Well, if we look at the learning target, opposite charges attracting and similar charges attracting is part of Coulomb's law. And when those charges interact with one another, you get attraction or repulsion, which are the electrostatic forces. So what she did show me in her model is an explanation, a prediction, a description that was clear and accurate of the electrostatic forces. But she only showed me one piece of evidence. And to me, she's able to use the Van der Graaf generator and the PyPans as a piece of evidence. She didn't just state the concept, she actually shows how it's happening. So when I grade her work, I can say, okay, she's not going to be a 3, she's not going to be a 2, she'll be a 2.5. Now, what I noticed when I looked at her work closely is that she started using words like, now she's an English learner. She said they each attain the same positive charge polarity. I never taught her polarity. So maybe some of these ideas might be borrowed from Google. And that's the benefit of using multiple assessments to measure the same learning target. If you see consistency throughout each assessment, then maybe this is her understanding. If you see a sharp decline, then I might think she did copy someone and plagiarize. So that's one of the strengths of using multiple assessments to measure the same learning target. What did the balloon and hair assessment task look like? Well, I show them this video of Coulomb's law happening between hair and balloon. The balloon and the hair generate some friction and build up charge. And as a result, there is this interaction that students can see visibly. How did she explain it? She showed representation. She wrote an explanation. At the beginning, nothing happens. And then when one object rubs against another, and as the balloon's pulled away, the opposite charge on the hair causes it to be attracted to the balloon. The balloon and his hair stick together and his hair stands straight up and he doesn't need to hold the balloon. The balloon at one point in the video just sits on his head. So this shows me that she does understand that opposite charges attract. But what she didn't show me is that similar charges repel. So if we're using this rubric, it's very clear to me that she did not give a complete, clear, and accurate description of the electrostatic forces. So she's back to a 2. And the one piece of evidence is the hair and balloon. So far I'm tracking her understanding. It's at a 2.5 to 2. Assessment 3 is the Scotch tape activity. And I'm going to go ahead and skip these videos because you might have seen them before. Question 5 in activity 2 is use your observation of the tape activity, magnet test, and patterns you identified to explain what happened to the pieces of tape. So she's able to clearly say that 2 strips of tape have the same letter, TT and BB, because the same letter equals the same charge. They will repel and push apart. Another case, when the 2 strips of tape have a different letter, BT or TB, come together, different letters equal different charges, they will attract and stick together. As her teacher, I see a very clear and accurate description between 2 objects that have electrostatic forces between them using opposite charges, attracting, similar charges, repelling. And the 3 pieces of evidence are going to be the 2 T tapes, the 2 B tapes, the B and the T, and then the T and the B. So I'm able to use this rubric to help me assess more fairly, did she meet the standard of, did she meet the learning target? Yes, in my mind. As a professional, I decided that's what she's going to get, a 4. Can she do it again? Well, I have her revise the tape explanation, but this time as a model. And I see your hand, Ms. Fuentes. I'm just going to finish this one point, and then we'll go straight into your question. Lam is able to represent her explanation as images and reiterate her understanding. 2 opposite charges attract, 2 oppositely charged objects will attract and stick together. Same positively charged objects will repel and push apart. Same negatively charged objects will repel and push apart. Very consistent. I see her with 3 pieces of evidence and a clear and accurate description, 2.5 to 4.4. Okay, Ms. Fuentes, you had a question.
Yes, Mr. Lim, thank you.
Yes.
So I noticed that the student was not using the vocabulary electrical force,
Electrostatic attractions?
electrostatic,
Yes.
and you gave her a 4. I was just wondering about.
Well, I was looking for a description of the forces and a prediction based on her understanding of the forces. So maybe that's where I could use some improvement, is the actual implementation of the vocabulary. But since she's able to use the most foundational, like student-friendly language to demonstrate her understanding, I gave her a 4.
Oh, I
And
see it. It's you said describe and predict, not
yes,
explain. Using,
yes,
okay. Okay,
yes.
thanks.
So that was a great question. And I'm still learning from you guys. Okay, so how do I do a overall score for this student? Well, in my certification process, like the 8 hours of asynchronous work, I was taught that when you have current scores outweighing past scores, plural, then you can go ahead and allocate a grade, a subjective allocation of the grade that they are proficient or not proficient. And it does make sense because we're just measuring a learning target. We're not taking averages or medians. We're just looking at what would make most sense when it comes to mastery of the learning target. She's no longer at a 2. She is at a 4. For Unit 2, learning target 8. This is how I assessed another student, William. 5 assessments to measure learning target 8. Where is learning target 8? Here it is. I can develop a model to illustrate the release or absorption of energy from a chemical reaction system that depends upon the changes in total energy. Well, according to my rubric, the model is either incomplete because it does not illustrate the release and absorption, and it does not explicitly identify any components. If William gets a 2, it's because there's some illustration and an explicit identification of components, but no relationships and no connection. If William gets a 3, that's because he clearly and accurately illustrates the causes of the release and absorption of energy from a chemical reaction depending on the changes in total energy. He successfully identifies and describes the relationships between components, but does not connect it back to the phenomenon. A 4 does everything 3 does, but connects it back to the phenomenon. Let's look at some artifacts. The artifacts will come from the Van der Graaf and the finger interaction, where the finger lights the Van der Graaf, the finger lights the Bunsen burner. Another assessment is when I decided to show the balloon explosion to my students earlier, just so that I can get them thinking of the anchoring phenomenon. Why do things explode when there's a small spark? Assessment 3 is going to be the bow and arrow model. Assessment 4, I created, it's a bowling ball being rolled from a person and how that can demonstrate the learning target, portions of it. And then the final assessment would be the explosion of the balloon filled with rocket fuel model. William watches this video in Unit 2, Investigation 1. The finger lights the Bunsen burner. This is his model. No written explanation accompanying this model. So he does illustrate some cause, right? Electric energy goes into the Van der Graaf, into the arm, into the Bunsen burner. He identifies some components, right? Electrical energy, Van der Graaf generator, but he does not explicitly describe relationships or connect it back. So he gets a 2. But it doesn't stop there. William knows he has multiple opportunities to attain the learning target. The balloon explosion we were looking at earlier. Here's his explanation. When the flame is brought closer to the ball is filled with gas, and so that means that the gas in the ball will expand, because we learned that when some objects are heated, they expand, like railways or electric wires, and that is what causes the explosion. Here's his components. Here's the relationship. The ball will expand when objects are heated. So there is some achievement here in portions of the rubric, but for the most part, he does not clearly and accurately explain the causes of the release of energy. If we're looking at the standard, it goes back to the breaking of bonds and the formation of bonds that is responsible for a release of energy. So he gets a 2.5. Next assessment, William gets another chance. Explain this, William, in terms of release of energy. He finds 2 Google images. Obviously, he's not copy pasting anything, but he comes up with the statement, potential energy is transformed to kinetic energy. Well, that doesn't really show me the transformation, but it does give me an idea. He knows that one relationship is happening between the 2 types of energy. So he does explain a release of energy, and the release came from the buildup of potential energy. So he's stuck at it too. The bowling ball phenomenon, this is something I found online because I wanted students to be very clear when they describe to me where kinetic energy is coming from. So I made this template, and I will provide this template also when we post our video today, that students need to show me on these bar graphs what's happening to the potential and kinetic energy, then describe what's happening. And William successfully does that. These were all blank, and he's able to show me potential energy decreases at one point and is released. He did it at the wrong time, because obviously up here is when the potential energy is the highest, but he does have some understanding that kinetic energy comes from the potential energy as the bowler raises the ball from the ground higher and higher. So he does illustrate some of the causes of the release. He does show me a relationship between the components, and he clearly connects it back to the phenomenon. But what did he leave out is that the buildup of potential energy is due to the change in elevation of that ball. He was not showing me his understanding that it was about raising the ball away from the center of the earth to create that potential energy increase. And you can see that right there, it's inconsistent. And so he will not be getting a 3 or higher on this phenomenon. So that's where we left off at the beginning of, not the beginning, but right before spring break. I would love to see how my students do developing a model at the end of Unit 2 that explains what's happening to the chemical bonds, and then I can give a overall score that would represent how far he's come. But if we're just looking at assessments 1 through 4, he'd probably get a 2. So what do we do with this information now that you've learned about learning targets? Maybe consider using them to track your student progress and grade with more equity. Use or create new learning targets if you want to get yourself and students to focus on common expectations. Align or create new assessments, probably easier to align, to measure the proficiency of the learning targets. Use your professional judgments. Don't depend on averages or medians for an overall score, because students might be having, they might be going through something at home. There might be something wrong with the assessment itself. We're teaching online. Try to be reasonable with your professional judgment, because it's your class, and you can justify your judgment using the tracking system here. You can use this as evidence of your decision, and then input those scores into your grade book. So we are out of time. Thank you all for being open-minded and listening to what Adam and I have to share. And you're free to go. We'll post this on Schoology, the interaction group updates. We'll take questions if you'd like to hang out for a bit. I will have to leave in about 10 minutes. It's my birthday, everybody.
Thanks as always, guys.
Happy birthday!
Thank you.
Happy birthday to ya. Happy birthday to ya. Happy birthday.
Happy birthday!
Thank you, everyone. Thank you so
Happy
much.
birthday.
Thank you.
Feliz cumpleaños.
Muchas gracias. All right, everybody. I'll post this slideshow in the Schoology update as well.
Bye-bye.
Bye. Oh, that's a good point, Flint. Thank you.
Yeah, I'm just saying that you can't light a balloon of steam with a match. That's all. Because
Yeah.
you can't have a balloon of steam unless it's over 100 degrees.
Mm.
Yeah,
It's hard to do.
It's not gonna light, it just pops like a normal balloon pops.
This what I'm saying. It is a normal balloon, and
Yeah.
unless you're like actively generating the steam right then. If you held it on and we're currently collecting steam, then it would be a balloon of steam. It's not. It's a balloon of air. That's all. Don't worry about it. It's not a big deal. Thank you so
Yeah.
much. I really appreciate the mastery grading rubrics and tips.
It's very new, isn't it?
I think that's going to make a difference if I can get that going.
Yes.
Thanks so much.
Thanks for coming, Flint. See you next week.
So soon. Bye.
Yes. Bye-bye. Okay, Adam.
All right. No questions.
Yes.
Enjoy your birthday, Mike. Did you get your car yet? Is that
I did get the car. Yes. Thank
all
you.
right? Happy birthday.
Thank you so much.
Yeah.
When the pandemic's over, I'll take you for a spin. 0 to 60.
All right.
All right. I'll see you Saturday.
Saturday. Yeah.
Bye.